We shall go through solving this interconnected body problem with a force acting at an angle. Let's read the question. A 100 Newton force pulls two interconnected masses as shown in the figure. So there's the 100 Newton force, and there's the two interconnected masses. The kinetic friction coefficient between the surface and both blocks is 0.5. So we can use that to find out the friction force. Now the first thing that we need to do to solve problems like this is to resolve the force into horizontal and vertical components. In order to do that, we can draw our parallelogram around the vector with horizontal and vertical sides, and we can find the size of the vertical and horizontal sides. Fy will be 100 times the sine of 30 to give us this length. Therefore, the upward component of the 100 Newton force, that's 50 newtons. And Fx, or the horizontal component, is 100 times the cos of 30, and that gives us 86.7. Or actually 87, because we're given the sine and the cos. Let me just correct that. Okay, now in order to find the other forces that are the friction forces acting while this is being dragged along, we need to utilize the friction coefficient, or the kinetic friction coefficient, of 0.5. So the friction force is equal to Fk equals nu kinetic times the normal reaction force. So in order to find the friction force, we need to find what the normal reaction force on each of these two masses. So looking at a free body force diagram for the 4 kilogram mass, we know that gravitational force pulls it downwards with 40 newtons, and thereby there must be a normal reaction force equal to also 40 newtons. Okay, so looking at the 6 kilogram mass, we also have a gravitational force found by the mass times g, which is 60 newtons, but the normal reaction force is not 60 newtons in this case. Why? Because the applied force has an upward component of 50 newtons, thereby lifting the mass up with a force of 50 newtons. So the mass is not pushing down with the force of 60 newtons on the surface. In this case, the normal reaction force will be 10 newtons. Why? Because 50 newtons, the upward component of the 100 Newton force, 50 newtons upwards plus the 10 newtons normal reaction will now equal the weight of 60 newtons. Since both of these masses will move along the horizontal, the vertical forces must be balanced. In this case, the weight is 40, but there are no other upward forces acting. 40 newtons is the gravitational pull of the Earth downwards, and so the mass pushes on the surface downwards with 40 newtons, and therefore the surface reacts with a 40 Newton force upwards. In the case of the 6 kilogram mass, it's not pushing down with 60 newtons on the surface. Yes, it is being pulled down by gravity, but it's also being pulled up by the 100 Newton force by an amount equivalent to 50 newtons. And thereby, the mass pushes down only with 10 newtons on the surface. And therefore, the surface reacts with a force upwards of 10 newtons. So that's the normal reaction. We can now use the two normal reaction forces to find the coefficient of friction, or to find the friction for each of these two masses. Let us consider the 6 kilogram mass first. The coefficient of kinetic friction for the 6 kilogram mass is equal to, the friction for the 6 kilogram mass is equal to the coefficient of kinetic friction, which is 0.5, times the normal reaction force on the 6 kilogram mass, which is 10 newtons. So 0.5 times 10 gives us 5 newtons frictional force. Obviously, this will act in the direction to oppose the motion. So it will act towards the right. That will be 5 newtons. There's obviously a frictional force due to the 4 kilogram mass. That is found in a similar way. So the friction force of the 4 kilogram mass is equal to the coefficient of kinetic friction, which again is 0.5, times the normal reaction on the 4 kilogram mass, which is 40 newtons, thereby giving us a friction force of 20 newtons. So this friction force acting here is slightly larger, and it's 20 newton. We now know all the forces acting on the bodies, in fact, on the system of interconnected particles. We have an applied force, which has the horizontal component of 87 newtons. We have a friction force acting to the right of 5 newtons. Another friction force of 20 newtons acting on the 4 kilogram mass. And those are the only forces acting along the horizontal. The forces acting along the vertical must balance out, so 40 balances out with the 40 down here, and the 60 newtons upwards balances the weight in this case. So we can ignore the vertical forces since we're interested in the horizontal acceleration, and the vertical forces are perpendicular, therefore have no effect. So in considering the horizontal acceleration, we need to see what the net force along the horizontal is. So 87 newtons acts to the left, and 5 and 20 newtons act to the right. So the net force along the horizontal are 87 minus 5 minus 20, which gives us 62 newtons. Since we know the net horizontal force, we can therefore find the acceleration along the horizontal, which is equal to F net over mass. Now the net force of 62 newtons accelerates the whole system, and therefore accelerates 10 kilograms of mass. And so the acceleration is therefore 6.2 meters per second squared. The next thing that we need to know is the tension in the strings connecting the two bodies together. Now to do that, we have to look at a free body diagram for one of the masses only. So let us concentrate on the 4 kilogram mass. It's acted upon by the weight and the normal reaction, which cancel each other out. But along the horizontal, it's being pulled to the right by the friction of 20 newtons. But the tension in the rope causes this mass to be pulled to the left. So let's apply Newton's second law to the 4 kilogram mass. Okay, so let's look at this here. This is the application of Newton's second law to this system here. T1 must be greater than 20 newtons. So T1 minus 20 is the net force. T1 minus 20. And that net force equals mass times acceleration. So that net force, T1 minus 20, is accelerating a mass of 4 kilograms. We're concentrated here. So that mass is 4 kilograms. And the acceleration that it gives it is 6.2 meters per second squared. We found that by considering the system as a whole. That gives us a tension force, or 44.8 newtons. I think that concludes finding all our unknowns.